different depending on which planet you are on. However, your mass never changes. You could also be flying through space, you know, far, far in the depths of the galaxy, but far away from any mass, any star. You still have mass, but you will not feel any weight. In fact, what you feel normally is the normal force pushing up on you. That's not what we're going to talk a little bit about today, is the normal force. Then, I know a lot of you already read through the friction, which that's great because we are going to discuss friction and start solving some problems on friction tomorrow, or today even. And when we don't finish there, we'll wrap up tomorrow. So here we go. These instructions, I believe, tell you to draw the free body diagram where if you are, what does it say here? You're on some sort of platform or whatever. You have a jet-powered flying platform. Sounds pretty cool, like an actual hoverboard, like a real hoverboard, not those things that have wheels. Anyway, it can move straight up and down. For each of the following cases, draw a free body diagram with accurate relative vector magnitude. Write Newton's second law in the y direction, solve for n, and make a statement about the apparent weight of the rider. Okay? So here's the ground down here. Here's you and your super cool jet-powered hoverboard. Okay?
Wait, so since it's on the hoverboard, their apparent weight would never be 0, right?
Well, they're on the board. Their apparent weight we're going to figure out what their apparent weight is. What they feel. Do they feel heavy? Do they feel light? Do they feel normal? Do they feel like they're floating? Okay? And so there's some jet engines down here. All right, so we can draw some planes. Something like that. Anyway, whatever. But that would kind of, I don't know if I'm gonna draw the planes because that almost makes it look like you're like it's gonna be thrusting upwards. I guess it is in a little bit. Alright, so we need to draw a free body diagram for you. What forces are acting on you? Weight, okay, the weight due to gravity.
Normal.
And normal. So what would that free body diagram look like?
Wouldn't it be equal because it's hovering in midair, so it
Yeah,
wouldn't be moving?
Yeah, you're hovering. It's the same exact situation as if you were standing on the ground. Okay? In terms of you're not accelerating upwards or downwards or even moving with any velocity upwards or downwards. So yes, absolutely. Normal matches weight. If we write Newton's second law, we would say the summation of forces in the y direction is the normal plus, we'll put a negative w since it's in the negative direction, equals the mass times acceleration in the y direction. Is there any acceleration up or down?
No.
Nope. So that whole term goes to 0. The acceleration is 0. Mass times 0 is still 0. They want us to solve for the normal. So this goes to the other side. So normal equals weight. Make a statement about the apparent weight of the rider. How does that rider feel? Does he feel heavy? Does he feel light? Does he feel just like he always would? He's just standing there. The platform is also just sort of hovering there.
So it would be normal, wouldn't it?
He would feel normal, although I'm going to try not to use that word because it gets confused with the normal force.
How would you say it?
Just feel this the way that he always would, as if he was just standing still on Earth. So, feels
The same as us.
the same as if on Earth. Not moving upwards or downwards. Alright, Kevin, at some point you gotta cut your losses, grab a spare sheet of paper and start copying this down on that. Alright, you are ascending and speeding up. So now we can draw the planes. So we've got velocity is upwards, and the net acceleration is upwards. velocity is going upward. Net acceleration is upward, okay? And what does that tell us about the direction of the net force? Say again? Also upward, since the net force and the net acceleration have the same direction. So when we draw the free body diagram, there's still just weight and normal acting on you. Still just weight and normal. Now, what if someone said, well, isn't there also thrust?
It's not acting on you, it's acting on you.
That is correct. The thrust is acting on the board. It's the, if we think about just what's coming in contact with you, it's the weight force due to gravity and the normal force of the board.
So would the thrust action on the board increase the board's normal force action on you?
Yes.
Okay.
So, your weight is still pushing downward. Since we know that there's a net force acting upwards, how am I going to draw this upwards normal vector? Up, larger, smaller, about the same as the weight? Larger, yeah. Unfortunately, I don't have those. So there's the normal force going up. Newton's second law, summation of forces in the y direction. It's the same as before. Normal plus negative weight equals mass times acceleration in the y direction. Is there acceleration in the y direction? Yes, there is. So this term does not go to 0. I'm just going to leave it as mass times acceleration in the y. Solving for the normal is, puts both sides, weight plus mass times acceleration in the y direction. So compare that, n equals w plus ma, with this situation over here, normal equals w. So what's the difference in the normal force?
You're adding mass and acceleration.
Yeah, I'm adding that mass times acceleration, okay? So this person feels more of a normal force acting on them. Makes sense because the thrusters are pushing the hoverboard, so the hoverboard's pushing you, or the flying jet-powered platform, or whatever. Okay, so what does this person feel? They feel heavier, okay? Alright. Now, if you've ever, I think we mentioned this last week, when you are rising really fast, what does it feel like? You feel like you're being pushed downward, okay? But in reality, what's happening is you're being pushed upwards really fast. It's one of those interesting sort of counterintuitive things. The board is actually pushing up into the person. So that's why we say what you feel is the apparent weight, so to speak, is pretty much determined by the normal force. Well, we say, oh, I feel really heavy. Well, that's because the normal force is pushing you up more. All right, next situation. And once we get these two, it'll go a lot faster. You are descending and speeding up. And so when I mean speeding up, it means going faster and faster downward. So here you are on the hoverboard. So your velocity is downward. Your net acceleration is downward, so therefore the net force also downward. Speeding up meaning you're going faster and faster, that means the velocity and acceleration are in the same direction, yes. So there's your weight force, same as always. Normal force, smaller, larger, about the same.
Smaller.
Smaller, you are correct. So Newton's second law, summation of forces in the y direction. Normal plus negative weight equals mass times acceleration in the y direction. Now this is interesting.
Cause it's gonna be the same thing.
Normal equals, if I put that plus over here, weight plus mass times acceleration in the y direction.
That's the same.
Yeah. That, something doesn't feel right about that. What would you feel in this situation?
With your lighter?
Yeah, you feel lighter. This is when you are falling down initially, you get that butterflies in your stomach kind of feel. Well, something doesn't seem to match up right. I know what it's, I'm not feigning ignorance here. I am feigning ignorance. Anybody have an idea why those two, I mean, are we missing something?
Your values would just change.
They would change. What value would change? Acceleration, yeah. In this case over here, acceleration is negative. So this would essentially be the weight minus the mass times acceleration. Over in this one, the acceleration is positive, so it's truly a plus situation. Over here, it would be a minus. And so that's, once again, the normal force is a little bit smaller than just, notice, let's say normally your weight was 100 newtons, okay? So here we're having 100 newtons, which you would normally feel on Earth, staying still, minus something. So when you feel lighter, it's because your normal force is smaller. You feel heavier, it's because your normal force is heavier. Okay, I think that's enough of those situations. Let's go ahead and turn the page. Just kind of wanted to, oh, there's a jet-powered picture thing there. Platform, I guess. So here we go. Suppose you have a hand pushing down on a book on a table. All right. So, or you can push down on your book or on your MacBook or on your binder or on your paper. So push down on that. Okay. For each of these cases, and we're just going to do a few of them. Draw the free body diagram with the accurate relative vector magnitude, write Newton's second law, and solve for n. So if the hand is not pushing on the book, that's, so just imagine the hand's gone. That's real easy. Weight going down, the normal force from the table going up. It's just what we've summed before. Summation of forces is normal minus the weight, mass times acceleration in the y direction, which happens to be 0. Normal equals the weight force. What about if the hand is pushing on the book with 5 newtons?
Along with normal force.
Okay. So yep, you all are saying lots of good things. So there's the weight force. We now have the hand force. Okay, this is your external force or whatever. So I'll make that a little bit more than the weight, I guess. So let's say F external, which is 5 newtons, okay? All right, now what about the normal force? Obviously it's going up. Should it be shorter than the weight, longer than the weight, or about the same as the weight? Longer than the weight, okay, how much longer?
The same amount as the external.
Yeah, so should it be exactly, should I like just reflect that external force? So you're saying, so here's the question. You would combine them,
Oh, yeah.
okay? Because this normal force has to be going up exactly,
The same amount as both.
those things are going down, okay? So I guess I should have,
If you canceled out the external, you'd still have the weight.
right, and that means it would be like falling down. Yep. So I guess I maybe should have written that the net acceleration is 0, which therefore the net force is also 0. That means everything has to balance out. So the summation of forces in the y direction is,
Normal minus weight minus external force.
yep, I'm gonna put, yeah, we should put F external. equals mass times acceleration in the y direction. Now in this case, mass times acceleration in the y direction. What's acceleration in the y? We already said it was 0 based on observation there. 0. So therefore the normal force equals the normal weight force plus the external force. So this is the algebraic symbols of what we kind of reasoned out when we drew that normal force higher. It does. External. The next. Okay. What I wanted you to kind of see from this is that it's almost like the normal is reacting. We talked about this sort of in vague terms the other day. Like, I can't remember who I chose that said, you know, everybody look at your book, look at the MacBook, see the normal force going straight up. Now push on it, and look at, but that normal force just, you know, increased dramatically. It increased the exact same amount that I was pushing down on it, okay? So sometimes we might say that the normal force sort of like is a reactionary force. It reacts to the situation, and that is the case. You can't just always say, oh, normal force equals the weight, because it doesn't. In fact, I think a couple of y'all asked me that. I said, no, the normal force does not always equal the weight. The normal force, you have to calculate it based on the weight, based on whether or not it's moving up or down, whether or not it's accelerating, okay? And also, if there are things literally pushing or pulling on it, okay? So, quick question. What if that 5 was turned into a 20? Just, instead of 5, this would be 20, okay? That's no big deal. I think we can handle that. What's interesting, though, is number 4, where it says, the hand is lifting up on the book, but not enough to lift it from the table. It's not doing any work, it's not moving it, but does that mean that the force is not existent? Yeah, the weight, so it's, let's see, so what would that look like? So here the hand is lifting up on the book, okay? So the hand is pulling up, but not enough to lift it from the table. I'm going to specify and say just enough so that if there's any more lift, and if it pulls up any more, then it will lift it up off the table. Okay, but we'll say it's just enough, not enough to lift the table, but just enough so that any more force would lift it. So you're holding it just enough so that if you were to add just a little bit more, it would start accelerating. Does that make sense? So you're holding it, you're pulling up just enough. Yeah. So how else might you describe that? Well, if the weight is going down, okay, and I've got the normal force going up, and my external force is also going up since I'm pulling up on it, okay? All right. I'm going to try to draw this to scale. What I'm getting at is that if I'm lifting it up so that it's if I'm lifting it up so that just a little bit more and it's going to start flying off the table, what is the normal force at this point? If I'm lifting it up,
what is the number is 0?
yeah, it's 0. So I'm lifting it so that the normal force is 0. In other words, I'm doing exactly what the table is. If the table's pushing up with 8 newtons, okay, I'm going to pull up with 8 newtons, okay? If I pull up with 8 newtons, it's still going to stay here, and it's going to barely be in contact with the table, but the table's no longer pushing up on it. It'd be exactly the same as if I did this. It's just, I'm able to slide it right there, still no change. So the normal force, I'll put a little arrow here, is 0. And that is a thing, it can happen. So the net acceleration is 0, which means the net force is 0. So summation of forces in the y direction, we have F external plus the normal minus the weight equals,
Would we have to count normal? Like, if it asks us to do it, like, let's say in our mastering physics homework and it says, do the second law, would we have to count normal, even though it's not acting on it anymore?
I might set it up, and then at this point, then I would say normal is 0, and mass times acceleration is 0, and so therefore the external force, that really does look like TTs. Configuration's not playing along very well today. Is exactly the same as the weight. So like I said, it's the exact same situation as if I were holding it here. That's kind of what I was trying to get at with that one. Alright. This one, the hand is pulling the book at a 30-degree angle to the horizontal with a force F. We'll say pulling up 30. So there's the book. There's F, we might as well say FXT. 30 degrees. I'm pulling up on it, but it's really not moving at all. I'm just kind of pulling up. The question is, how does that affect the normal force? So we'll draw the free body diagram. Weight's going down. Normal's going up. I'm going to make the normal a little bit shorter than the weight though, okay? Because we also have an external force, but notice it's at 30 degrees. And we don't like things in the first, second, third, fourth quadrant. We don't like that. We want to resolve that into its x and y components, okay? So, anybody know what's the value of the horizontal vector?
30. Cosine 30 times the force.
Okay, so F external cosine 30, and the y component, F external sine 30 degrees. So now when I write Newton's second law, summation of forces in the y direction, what's going up? Normal plus the y component here, F external sine 20.
What was it, 20?
30
Oh, okay.
plus negative weight equals mass times acceleration in the y direction. Still not moving, so acceleration in the y direction, that's 0, that whole term goes to 0. So now I'll move these two to the other side. Normal equals weight minus F external sine 30 degrees. So talk to me about how this book feels as I'm pulling on it with an upwards angle. How does it feel? Based on that normal statement right there. Feels what? its normal force is a little bit less. It's weight minus the amount that I'm pulling up on it, okay? So it's going to feel a little bit lighter, okay? All right, now, that's going to affect some other things that we're about to find out. So, I'm pulling it up, its normal force is a little bit less. That can be kind of helpful, okay? Because I might, we'll find out here in a second, the friction that an object feels, the friction force, depends on the normal. Okay, I'm gonna say that again. The friction that an object experiences depends on the normal. So, if I'm pushing down on this and trying to pull it, there's gonna be more friction than if it's just sitting there by itself and I'm pulling it. And there's gonna be even less friction than if Kevin was over here kind of pulling up ever so gently on this, okay? Come on, Kevin. Pull up ever so gently, not enough that it's actually going to lift off the ground. I know with your strong muscles, that's gonna be hard to do. Yeah, I know, see? He's pulling up, but now I can pull it. Oh man, look at that thing. That's so easy. It's just flying. Follow me. Good job, Kevin. So, I guess here's a little pro tip. If you ever have to carry something heavy, but the other person is not really strong enough, maybe you need to slide it, it's not strong enough to lift it up, okay? Just say, hey, you don't have to lift it up, just push up on it, okay? That's all I want you to do, just push up on it while I pull it, okay? Because if you can't even move it because it's so friction, if they push up on it, then that's going to make the normal force smaller because they're pushing up on it, and then that's going to make a smaller friction force, and you might be able to pull it and get it going. Okay? Hopefully you're never in that situation.
Mr. Gardner,
Yes.
would there be any kind of like static friction on the book since you're pulling it at 30 degrees? Shouldn't it be sliding?
Oh, good question. Yes. So wait a second. If I look at the horizontal
Is that your static friction?
summation of force in the x direction, yeah, it looks to me like there's just me pulling on it, right? F external cosine 30 degrees. Why is this thing not moving?
Because static friction is going to the negative.
Yeah, because there's static friction which is pulling it the other direction. Let me see if I can get my block to show y'all. Everything's always blocked, so I just found it easier to get a block.
Oh, yeah. He really does have like a block.
Alright.
Well, I mean, it used to double as my pen holder. All right. So yeah, let's start talking about friction because that's the next thing here. So let's think about what's going on at the smallest level if I start to push this, but I don't push it very hard at all. Okay, so I'll push it up, but it's not moving. What's going on? I am pushing it, I am applying force. Okay, there's static friction. Why? Why is it not moving? Why? What is causing that static friction at the smallest level?
The friction?
Yeah, the friction, but like, what's causing that friction? Why can't, I mean, just try something moving on your desk, but just give it a super weak push. I mean, like, so that it doesn't even move, okay? All right? Why is it not moving?
I'm not strong enough.
The way
Push it up, kind of push it completely horizontal.
Is it a weak?
Push-
That was weak.
You're pushing it too strong. Push a little bit less, but not so much that it actually moves. Why not? Why is it? I'm pushing on it. Oh, there's moving. Okay, what? Static electricity or something, or static friction? Okay, yes, that is a word describing the phenomenon. But what is causing it?
the way,
The roughness.
the texture of the
Mm-hmm. If we're, what our eyes see is that, but to the dust mite, this is a dangerous, perilous, amazing, jagged world full of mountains and valleys. Okay, that's the table, and this is the book. Okay, I know. Don't just stay calm. All right, it's a scary place. at the microscopic level, okay? So imagine you were trying to push the book. Now this goes on over the entire surface, okay? And so so it's almost kind of, they're almost going to interlock right now, but as you start to push, it goes, you know, it's like, right? In fact, if you don't push enough to break off the peak there, okay, or to rip this molecule off, okay, then the book's not going to move, right? Now, also what happens is that you have these guys, some of, you know, at the smallest, you know, at the molecular level, some of these particles over here, maybe if they're like positively charged, these are negatively charged, then they also kind of want to be like, hey, let's get a little bit of magnetism going on here. Well, not magnetism, but electrostatic attraction. Anyway, we'll learn about that in chapter 20. Anyway, so they're like, no, I don't want to. But then you actually also have the pieces that you don't want to do that. So let's just say you have to give this book a 0.5 Newton force just to get it going. Does that make sense? All right. What if you need 0.5 to get it moving? What's going to happen if you give it a 0.1? It won't move. Okay. What if you give it a 0.2? It won't move. Okay. What if you give it a 0.3?
It won't move.
0.4? 0.5? It will start moving. Okay. But think about what those diagrams would look like. Okay. If the force that I'm giving, which I'm going to say is F, is 0.1, what does the free body diagram look like? Obviously, we've got normal. Oh, wait. Normal. I'm pushing it that way. So my external force is 0.1. What's the static friction force? She said 0.1. Would y'all agree with that? Fs equals 0.1. That way, now hold on, I should make it exactly equal and opposite, right? But what if I give it 0.2? What's the free body diagram look like? Weight going down, normal going up. I'm putting a force of 0.2 on there. What's the static friction force going to look like? You just said it was 0.1. Wait, it's equal and opposite. All right. So I push a little bit harder. Okay. These things, they might start to move here, there, but they're still holding on. Okay. So you are correct that the static friction force in this case is 0.2. What if I give it a I give it a push at 0.3 newtons? Kevin, question.
If let's say you need 0.5 to push the book,
to get it moving.
To get it moving.
Yeah.
Why wouldn't you draw a vector the length of 0.5 and then static vector of 0.1?
Because I'm wanting you to see that the static friction force is kind of like the normal in the sense that it reacts. Okay? It's not always going to be 0.5 newtons for the static friction force. It's not always going to be 3 newtons or 0.2 newtons or whatever. It depends on how hard I'm pushing. Does that make sense? So if I push with 0.1, it's going to push back with 0.1. I push with 0.2, it's going to push back with 0.2. Do you see what I'm saying? All right. I push with 0.3, it's going to push back with 0.3. In fact, this is going to continue on. So static friction force of 0.3. Now, the reason all of this is the case is because we've already said that there's a static friction force maximum. Fs max. Okay? And we said that that was equal to 0.5 newtons. What this value actually is different in different situations. Now, here's a question for you. What do you think friction force depends on? Taking all guesses.
Depend on?
Yep, what does it depend on?
Wouldn't it be the same as static friction, like the surfaces in contact?
Okay. So, what do you mean by the surfaces in contact?
Well, like, you know, they have ragged features, so they're gonna stop themselves from moving, but in,
Okay, so you're saying, so the surface geography.
yes,
Okay,
but in this way, just friction in general, never mind, I thought it was kinetic.
yeah, well, it can be kinetic friction, static friction. What does it friction depend on?
What do you know?
The weight of the object?
Force.
Magnitude
The magnitude what?
of the force.
Of which force?
Of like pushing or pulling.
Okay. So I'm not saying these are right or wrong. I'm just saying, get them all down here. Magnitude of the external force. Keep going. Somebody else.
The surface geography of the object.
The what now?
Wouldn't it be like just the surface geography of the surface, but that of the object?
The surface what of the object?
Surface
The
geography.
same thing of like
Surface yard.
geography. is
Geography.
The
Okay.
same
so-
thing as the surface, but for the actual object.
Okay. So surface geography. Yeah. You know, for both.
Yeah.
Yeah. Okay. And the weight of the object. I'm like surface. Anyway. Okay. All right. Yeah. Does anybody have written down on their notes the formula for friction force?
Yes.
Yes.
Yeah.
I don't know how to. It's like
It's
like
the
a
U.
backward U. thing.
Yeah, it's
Coefficient
U.
of
But like,
force.
yeah, I felt like a.
Yeah.
The coefficient.
U.
And then with the little letter depending on what it is.
And then.
What does it say? Yeah,
Maybe
mu.
upside down. And
In.
Yeah, that's right. Mu.
Oh, that's a better way to see it.
Mu.
Mu.
Greek letter mu.
I thought mu.
Yeah.
No, that's not mu.
Oh, it's not?
Well, I'm sure it is, but
It might be, but it's not as determined. It's not.
Might be lowercase.
No statistics, that's not.
Oh, what do they call it in statistics?
It's like.
they
a
call it
mu.
something mu out.
Yeah,
I don't know if
it
it's
is
saying
mu.
mean or mu because it's just.
It is mu.
I don't know. It's an M.
Well, we'll determine our Greek later, but I might be wrong. I'm pretty sure it's mu, but I'm not totally sure. Okay, so
You're probably
I'll for now, it's this. This is why we say the friction is the fun formula, okay? For obvious reasons, okay? Both with static friction and with kinetic friction, you have this mu, okay? And mu depends on the surface geography, okay? So it depends on whether you have steel on steel or steel on, you know, wood or, I think, was there a little chart there in your book that showed all the different
Yes.
values of friction? Find that, oh, you don't have your books out.
You want the
Guess what?
coefficients of friction?
Oh, that's right. Yeah, the coefficient of friction. That's what that thing is called.
And it gives different materials.
Yep.
Or
It-
static.
Yeah, so there's values for static friction, so how much they're gonna fight if they're not moving. Yes.
that thing is mu or whatever. MU.
MU. Okay, so we've got confirmation. Awesome, thanks. That makes me feel better. Anyway, so yeah, you've got values of mu for how sticky those two things tend to be, which is how jagged are their peaks, okay? Is it like the Appalachian Mountains or is it like the Rocky Mountains? Has anybody ever been to the Rocky Mountains? Oh yeah, okay. How about like the mountains in like West Texas or like Oklahoma? Have you ever been to those mountains? They're kind of like, yeah, the hills, yeah. What about the Appalachian Mountains? Anybody ever been to the Appalachian Mountains back east, like North Carolina, Virginia, Pennsylvania, Kentucky? Anybody there? Okay, well I haven't been there. They're kind of, they're so okay. So they're rounded, okay. They're not like the Rocky Mountains are awesome. So the Rocky Mountains look, you know, they're like super sharp, you know, they're like crazy. All right, and then the Appalachian Mountains are like rolling hills, are sort of kind of like that. So if you could imagine, you know, if your surface of your of whatever you're looking at looks closer like this, then you're going to have a very, very high coefficient of friction, okay? Now, y'all said the weight of the object. That is partially correct, okay? But technically, what the friction force depends on is how much are those two objects being pushed together, okay? Because we already found out from earlier, the weight alone is not enough, okay? Because if it's just the weight, what if there's a hand pulling up on it so that it's just, they're not even, so they're just in contact but not enough?
So like the net force.
So it's like the net pulling down, that's the normal force. Normal force is a measure of how much they're in contact. Because what if you're pushing down on that object, okay? Then the normal force is gonna be a lot more, okay? So, Kevin, come over here and be a jerk. Push down on that stool as I try to pull it, okay? So the weight of the stool is still the same, right? The mu, coefficient of friction between the stool and the carpet, is still the same. But with Kevin pushing down, what has changed? The normal force. And guess what's going to go up by extension? The friction force. Okay, all right, here we go, Kevin. Oh, jerk. Trying to move the stool here, okay? So do you see what I'm saying? That's why it depends on the normal force as well. All right, if you look at that table, we will do some problems with those values tomorrow, as well as talk about why it's FS max. All right, if you don't have the notes, take them. If you're in NHS, we've got a meeting today in the library, lunch B, straight 12:30.
In the library.
In the library. Yes.
I made a prezi for like pounds or constant LBS.
Okay.
Yeah.
Yes, please.
She made a presentation.
Or something. No, he said he'd give me extra credit.